Hi everyone, welcome back. We're going to talk about the system design of Job Scheduler. This is a system that is used in almost every company, and because it covers a lot of different use cases. First of all, it can be used for cron jobs. Every company has cron jobs, and instead of running them in the Linux cron tab or elsewhere, you can use it for running different jobs at a specific type. Secondly, this system can be used for running any jobs that don't have to be executed in the real time or have to be executed at the specific time. For instance, if you upload a thumbnail on your YouTube, you don't need every single resolution of that thumbnail to be generated in the real time. This is something that Job Scheduler can be used for. You upload a thumbnail and then execute, let's say, 5 different jobs to create 5 different resolution for your thumbnail. And you can specify the maximum delay for the job. So you can say that, hey, this job has to be executed in the next 30 minutes or 60 minutes. This way, we have control over how long it takes for the specific job to be executed. If we talk about the thumbnail, for instance, we don't want to wait 2 days for it to be executed. We want it to be done close to the real time, but not in the real time. And that's the primary use case. So with that, let's go to the system design and talk about the different aspects of it. There are multiple ways we can implement Job Scheduler. In our case, we'll try to focus on scale. And as you can see on this diagram, we have multiple queues that are responsible for decoupling parts of our system. So let's go through the main workflow, high-level design, so we understand how it works. As you can see here, we have a front end. This is the service where all the jobs get scheduled to. The front end main purpose is just consume the job, create a message, and throw it to the queue. That's how we decouple the inflow of some jobs from the clients from the other part of the system where we consume and store and process the jobs. It doesn't matter how many jobs and how big the influx of the jobs is, our task consumer will scale if there are too many of them and try to consume and catch up on the queue as much as possible. So task consumer consumes the job and then does two things. First, it stores the executable into the AMSU storage or S3, and also create a record of the job in our sharded database. And then we have a task scheduler workers that constantly pulling the database for the tasks that have to be executed right now or can be executed right now. And then those tasks got thrown into another queue that decouples the scheduling part with the execution part. Then the workers consume the job or task from the queue and start processing it. As they are processing it, they constantly send the heartbeat and the status of the task into the status controller that updates the sharded database to make sure that if the worker dies or the job fails, that status ends up to be in the database and then the job gets in queued. So this is high-level design. Now let's go into the details. As the job comes into the system, it's going through the front-end queues and then end up into task consumer. The job of the task consumer is multiple things. First, it generates an job ID for the task. It uses that job ID to shard and partition data into the database. When we talk about the database, we can either use SQL or NoSQL database. If we use a SQL database, the whole question becomes way easier. We just have a simple schema that has a job statuses, job history, and then user jobs. And then we just index skills that needed to be queried on. If we decide to use NoSQL database, which would be more scalable, then we would likely need to think about how we want to partition our data to make sure that first we can pull all the jobs for a specific user. Then we can get a job history for a specific job ID, and then have a table that is easy to query for the jobs that have to be executed right now. We're going to look at the database schema in a second. So the data gets stored there, and then the actual executable file gets stored into the object storage or S3. Now let's think about the design for the NoSQL database schema. So as you can see here, first, as I said, we need to be able to pull a list of jobs per user. So one of the tables would be job table that would have user ID as a partition key and job ID as a sort key or a clustering key if we use Cassandra. So this way we can get a list of jobs for a specific user. The second table would be a job history. This is where we would have a specific job ID and different statuses that the job went through. So in this case, you can see it was running and then it failed. So based on the status, we would be able to find the jobs that failed or didn't finish and then in-queue them again. And the third table or the key would have to be something that is easy to query for the jobs right now, since our desk scheduler service would be polling database for the desks that have to be run right now. What we can do, we can have a different view on our Vita where partition key would be the timestamp of the job that has to be executed. So this way, when we want to get a list of jobs to execute right now and submit them to the workers, all we're gonna do, we're just gonna query by the timestamp and get the list of jobs that have to be executed. Then we send them to the queue from where they are consumed by the worker machines. Worker machine consists of multiple services. It has a controller, which acts as an orchestrator above the multiple executors that run on the same server. You can think about it as a orchestrator service and then containers or isolated environment that the server creates to execute different jobs. Controller pulls the tasks from the queue, and then the task is consumed by one of the executors on the server. As the job has been processed by an executor, every process sends its own heartbeat and task status to the status controller. It's done because if the executor dies or halts or the job fails, we want to understand that that process is lost and the job has to be requeued again. So in our case, if the executor fails or status controller stops receiving heartbeat from the executor, then the status stops being updated in the sharded database, and task scheduler understands that the job failed and it has to be re-queued for processing again. The biggest complexity of the system is the failure handling. For instance, we have queues in our system that decouple the parts of it. And when are we going to acknowledge the message? If we consume the message and then the processing fails or the executor fails, then the message will be lost. So the approach we're going to take here is to guarantee at least one delivery, which means when we consume a message from a queue, we are not going to acknowledge it until the job is actually done and Tuhatata key is returned. Only when that's finished, we are going to say that the message acknowledged and consumed from the queue. Otherwise, if the executor, for example, fails in the middle of the job, that queue will be consumed by different executor and will be retried again. As you can see on the screen, we have a state machine of the status of our job. So first, when the job written to the database, it has a status new. Then when the time of execution comes, the job will change the status to be unqueued. This means the job was sent to the queue for actual execution. When the executor consumes the job, will change the status to be claimed. So the job is claimed by a specific worker and executor. In case the worker or executor fails, at that time, the job will be re-queued because it stops sending heartbeat to our status controller. So the job goes back to being re-queued. Then as the job gets processing, in the middle of the processing, if the executor fails or worker fails, we can stop sending the heartbeat back to the database and the job will be re-queued. So the job scheduler service will see that the job status is processing, but there was no update for the last, let's say, 1 minute. So the job gets re-queued back to the system. And then in final state would be the success or the fatal failure. So this is the state machine that we're going to maintain in our database. As I mentioned before, it's a very popular system and employed in a lot of companies like, for instance, Airbnb and Dropbox use it. But there's still pros and cons of using it. One of the pros, of course, is that the system is very scalable. It has a clear separation of concerns. So a lot of microservices or other services don't have to manage their own cron jobs. They don't have to run different event loops to execute specific events or listen to the queue. All of this stuff can be moved to the job scheduler. Specific jobs, daily, weekly, or stuff that don't have to be done in the real time can be moved there. The cons of this system is that it's mixing ownership. Now, if I am a service developer and I have own the service, now I depend on the job scheduler. So if there are some issues with it, I will need to go to the team and try to troubleshoot. Hopefully they have self-service tools and I can figure it out myself. But if not, there's just more friction because product team don't have full control over the infrastructure. And the other big problem is that it's an overarching dependency. Now, a lot of different microservices, a lot of products depend on a single system. So in case there are issues with the system, everything's going to be impacted, all this job is going to be delayed or not executed at all. Yes, the system can recover, but the impact is going to be way more global and not local. So that's kind of second disadvantage of the system. But if it's properly maintained and have good self-service tools, I think it's a still good option to use. With that, if you like this video, I found it useful, make sure you like it and subscribe, and I'll see you in the next one. Bye.